Hello and welcome. It's wonderful to have you here as we set out to explore the exciting world of evolving deeper LLM thinking, a fascinating research paper by Google DeepMind, UC San Diego, and the University of Alberta. Today, we'll explore how large language models, often referred to as LLMs, can be guided to think more deeply about complex problems. For those unfamiliar, LLMs are advanced artificial intelligence systems capable of understanding and generating human-like text based on the vast amounts of data they've been trained on. They're the engines behind many of the AI applications we interact with daily, from voice assistants to language translation services. Specifically, we'll discuss an innovative approach called mind evolution, which employs evolutionary search strategies to enhance the problem-solving abilities of LLMs without the need to formalize the underlying problems. Now, formalizing a problem means translating it into a precise mathematical or computational form that traditional algorithms can work with. This process can be complex and time-consuming, often requiring expert knowledge. Mind evolution circumvents this hurdle, allowing LLMs to tackle problems that are difficult to define formally, but can still be evaluated effectively. You might be wondering, what exactly is mind evolution? Simply put, it's a method that uses principles from genetic algorithms to iteratively generate, recombine, and refine potential solutions to a problem. Genetic algorithms are computational search methods inspired by natural selection, the process that drives biological evolution. They work by evolving a population of candidate solutions over successive generations, selecting and combining the best candidates based on a fitness evaluation, which measures how well each solution solves the problem at hand. In the context of mind evolution, the LLM generates a diverse population of possible solutions to a given problem. These solutions are then assessed using a solution evaluator, a program that measures their quality and provides feedback. The model uses this feedback to refine the solutions, recombining and improving them over several iterations. This iterative process allows the model to explore both broadly and deeply within the solution space, increasing the likelihood of finding successful solutions. One key advantage of mind evolution is that it doesn't require explicit problem formalization. By avoiding the need to translate complex real-world problems into strict mathematical terms, mind evolution can address challenges that are difficult to define formally, but for which we can still determine if a solution is good or not. To illustrate the effectiveness of mind evolution, the researchers applied it to natural language planning tasks, specifically the TravelPlanner and Natural Plan benchmarks. Now, natural language planning tasks involve creating plans or solving problems described entirely in everyday language, without resorting to formal mathematical definitions. For example, organizing a travel itinerary based on a list of preferences and constraints expressed in plain English. Traditionally, LLMs have struggled with these tasks without the assistance of specialized algorithms known as formal solvers, which require precise problem definitions. For instance, using Gemini 1.5 Flash, a large language model developed by Google, only about 5.6% of problem instances in the TravelPlanner task were solved successfully with a single pass. A single pass means the model generates a solution once, without any further refinement. Even when employing a strategy known as Best-of-N, where up to 800 independent responses are generated and the best one is selected, the success rate only increased to 55.6%. Best-of-N relies on sheer quantity, generating numerous solutions in the hope that one will be satisfactory. However, with mind evolution, the success rates improved significantly. When controlling for inference time compute, which means ensuring that the computational resources used were comparable, mind evolution enabled Gemini 1.5 Flash to achieve a 95.6% success rate on TravelPlanner. Inference time compute refers to the amount of computational power and time the model uses when generating solutions. By keeping this consistent, the researchers demonstrated that the improvements were due to mind evolution itself, not just increased computational effort. In the meeting planning domain of Natural Plan, the success rate increased to 85%. Moreover, by employing a two-stage approach that utilized Gemini 1.5 Pro, a more advanced version of the model, for instances that remained unsolved after the first stage, mind evolution achieved 100% success on TravelPlanner and 98.4% on meeting planning. These results highlight how mind evolution outperforms other inference strategies like Best-of-N and Sequential Revision. Sequential revision involves the model refining a single solution step by step based on feedback, rather than exploring multiple solutions in parallel. Let's explore in more detail how mind evolution operates. The process begins with the model generating an initial population of candidate solutions. Each solution is evaluated, and those with higher scores are more likely to be selected for recombination. Recombination involves combining elements of different high-scoring solutions to produce new candidates, akin to how genetic traits are combined in biological reproduction. Additionally, small random changes or mutations may be introduced to explore new possibilities and prevent the search from becoming too narrow. An essential component of mind evolution is the use of a critic within the model. The critic analyzes solutions, interprets feedback from the evaluator, and suggests improvements. This creates an internal dialogue, where one part of the model critically assesses the solutions and another part works on refining them based on that critique. By fostering this conversation, mind evolution encourages more nuanced and effective refinements. To maintain diversity within the evolving population, the researchers introduced an island model. In this approach, separate subpopulations, referred to as islands, evolve independently for certain periods before exchanging high-quality solutions. This strategy prevents the population from converging too quickly on suboptimal solutions and helps explore a wider range of possibilities, enhancing the overall problem-solving capability of the model. Mind evolution's ability to significantly improve problem-solving performance without the need for formal problem definitions has important implications. It suggests that LLMs can be more effectively utilized in domains where formalization is challenging or impractical. By leveraging evolutionary search strategies, we can guide LLMs to deeper thinking and better solutions in complex tasks that were previously difficult for machines to handle. Furthermore, the researchers introduced a new benchmark called StegPoet to further test the method's capabilities. StegPoet involves encoding a hidden message within a piece of creative writing, such as an essay, story, or poem. This task is particularly challenging because it requires the generated text to convey the hidden message coherently and artistically, without explicit instructions on how to embed the message. Despite the difficulty, Mind Evolution achieved an 87% success rate using Gemini 1.5 Pro, demonstrating the method's versatility and effectiveness in diverse applications. In conclusion, the Evolving Deeper LLM Thinking paper presents a significant advancement in enhancing the problem-solving abilities of large language models. By integrating evolutionary search strategies and leveraging solution evaluators, Mind Evolution enables LLMs to explore and refine solutions more effectively, even in the absence of formal problem definitions. This work opens up new possibilities for applying LLMs to complex tasks in natural language processing and beyond, potentially transforming how we approach problem solving in AI. Thank you for joining me on this exploration of mind evolution and its contributions to advancing large language model capabilities. I hope this discussion has provided you with a clear understanding of how evolutionary strategies can enhance the depth and effectiveness of LLM thinking. Until next time, take care.